Hi, this is Professor Cummings, and I wanted to go over a really basic problem that I want to make sure we get cleared up, fairly early in the semester, to try and understand how to utilize a free body diagram. And so this was a problem on the quiz, and I thought it was a good one for us to discuss. Then which image is the appropriate free body diagram, for this particular image here? And to show you the options, what you have is A, B, and C, obviously. And you have different types of free body diagrams. And you can see there's slight differences between them. But you've got the basic structure. You've got these reaction forces, and then you've got the X and Y component broken up in X and Y components. And at A, you've got an X and Y component. For option A, at point A, you've got an X and Y component. You can see you've got the moment coupling of 800 pounds-feet. Here you have the load of 390 pounds, and it's X and Y component. And you also have the reaction at B. But which one of these options are appropriate? You can see at B, you've also got the same structure, but with, the same 390 pounds. You've got, a reaction here at B with an X and Y component. You've got a reaction here at A, which is only showing a reaction in the X direction. And when you look at C, again, you've got another reaction in the X direction. You've got a B with an X and Y component, and you've got a moment coupling happening at B. And you got an X and Y component here at the 390 pound load. So there's differences between these. And they're pretty substantial differences as far as being able to show the appropriate free body diagram. So what I did was I looked at this and decided, okay, now before we go on, let's try to define what exactly is a free body diagram. Alrighty, so I went and looked up the definition, an official definition, not just me winging a definition at you. And free body diagram. A free body diagram consists of a diagrammatic representation of a single body or a subsystem of bodies isolated from its surroundings, showing all of the forces acting on it. All right. Again, something very important. Isolated from its surroundings, showing all of the forces acting on it. So when you do a free body diagram, you're trying to break down whatever it is you're looking at, the beam, the crate, the body, and you're trying to get rid of all of the unnecessary components of the image that you're dealing with, and just seeing what is truly acting on that body so you can get a better understanding of it. And you use this in strength of materials, but also in kinematics, dynamics, statics, and even in machine design. You're basically, this is a tactic or technique that you're going to use a lot in engineering. And if we look at this, this image, just pay attention on the left first. What you have here is a incline at a degree of alpha, angle of alpha, a pulley, and you got two masses connected by a rope going over the pulley. So you got one mass, and this rope provides tension, and all we can assume is that there is some sort of pull between, so there's a tension between these two, and there are forces acting on it. So the free body diagram, again, if we go by the definition, we've isolated this body from all of its surroundings. We've represented the forces in the terms of the tension on the rope, the normal reaction force against the inclined plane, the weight of the crate or the body, and the frictional force pulling the other way. So we see it's isolated from its surroundings, and we are showing the forces acting on it. What else we've done is we have reoriented everything, and we put a new coordinate system onto the free body diagram. This helps us when we're trying to look at the sign, and when we sum things up in static equilibrium, we have some way of knowing what is adding to and what is taking away from in terms of forces, as well as any type of moments. And this orientation is based around this angle of alpha. So this is just another important part of a free body diagram. All right, so let's look at our original image again. So again, we got our image, and let's try to think, well, how do we turn this into a free body diagram? Well, first thing we want to do is want to identify the applied forces as well as the support reactions. The first part is fairly easy. It's only two applied forces, in this case a moment coupling, that's just spread out, given to you of 800 pounds-feet here at the 8 feet and 4 feet from the other side at this one point on this beam. You also have a 390 pound, and you're given an orientation of how that force is being applied. Now, the harder part would be the support reaction. Being able to look at this, this type of support and this type of support and understand what type of reaction is appropriate. How do we know what to make this appropriate so we can know what's going on in this beam? Another thing we want to do is establish the coordinate system, for static equilibrium in the direction of the forces. So that's where this comes in. So this way we will be able to say whether or not, this 390 pounds is adding to or taking away from, and what must be going on at A and B. So we can look and see how these reaction forces, support reactions, are responding and how they're affecting what's going on with the body. And that's where this, sum of forces in the X, sum of forces in the Y, sum of forces or sum of moments about, whatever origin should all equal 0 and their appropriate sign direction. So we're assuming static equilibrium. So what this really raises the question of is what is the appropriate support reactions, or one of the questions, support reactions, and how do we handle that? So what we have here is a list, of various support reactions. And you can see, these are the supports on the left, and over on the right, you've got the force reaction that we should expect, the unknown force reaction. And what you can also notice is in a lot of these cases, that the support reaction, may or may not be there depending on what is being applied. So what you want you to know is that they still have to be represented. So if the support reaction prevents a particular translation or rotation, there is a reaction force to be represented, even if that reaction force is just 0. So it's just there as a good practice. And then you can look at this and see that, when we look at things like the journal bearing or the thrust bearing, you've got a head stop in the translation for the journal bearing, which is going laterally. So you've got a support reaction going laterally. Now, if there's no lateral load or no load, that my shearing load on this beam, this could very well go to 0, but you do represent it. Over here, the thrust bearing, by its design, it stops you from going axially and laterally. And again, if there's no axial load being applied, this goes to 0, but you still have to acknowledge the thrust bearing is preventing translation axially. And when you look at this fixed support, again, this is where it's actually mounted into the wall. And when it's into the wall, it prevents you from going in the X and the Y. And because of the way it's fixed, it also prevents you from a moment. So there is a moment reaction. So that's what the different supports are showing you. So if we look at this image that we had before, we can start to try and put together what's going on with these support reactions. So we can look at this sensor down here on, or let's start with A, and think what is going on with this. Well, we can see that this probably most is represented by this smooth support, mostly because it's got some sort of wheel there, and it's at a particular angle. So we can start to look and say, okay, there's definitely a support reaction coming at, with respect to that angle that we need to address. When we consider what's going on at point B, you can see that's pretty clearly an external pin. So we can expect there to be, it's stopping the pin from going in the X and the Y, or the body from going to the X and the Y, but there's really nothing stopping it from rotating. And just from the look at this picture, I don't know what this image is supposed to be technically, but if you can see that this is able to lift off. If all that is just holding, simply supporting, a smooth support, that this may actually be designed to rotate about this. So there's nothing designed to prevent that rotation. So it doesn't have a moment coupling. So let's look at this and kind of break this down independent of our options. So we're going to create this, or think about this as a free body diagram. We're going to set up a coordinate system, and we're going to say it's in static equilibrium, right? So the sum of the forces in the x is 0, the y is 0, and any of the moments are going to sum up to 0. The sum of all the moments are going to come out to 0. And we're going to make it to the right positive, to the up positive, and counterclockwise or anti-clock is also positive. So we got that established. Now let's understand what's going on with the supports. So we said there was an external pin at B, and we can have the forces of F of X and F of Y. So we know that it's preventing translation, from going up and down and left and right. So we'll consider what's going on at A. If we look at that as just a smooth support, we can say, that it's going to have a reaction. And if we drew it as, and I should have drawn this as with the angle of theta, but I also know that if we go to, trying to sum up the forces in the X and Y, we're going to want to see the X and Y components at A. So we got A of X and an A of Y. And while we're at it, I went ahead and broke the 390 pounds into an X and Y component. So if we look at it through that lens, we know what the support reactions. We know what's going to generate a moment coupling. We can go back and look at our original question. So when we look at this, we can see that we do have an X and Y component for the applied load at A. So that kind of eliminates both of these two right off the bat. But we also know that because this is an external pin, that we shouldn't see a moment coupling at B. So that definitely eliminates, option C. So the appropriate free body diagram would be A. Okay, this is Professor Cummings. Just wanted to do this video for you. And if you have any questions, leave me a comment or share the video and go subscribe to the channel. And I'll talk to you later.